Hi, I'm Frank Marfi,
Hi, I'm Nicole Spencer.
and we're here to discuss technology apps and simulations. Okay, we're ready to begin. Do you want to present or you want me to present? We never
Um,
decided.
yeah, I can present, that's fine.
Okay.
Let me see here. Okay, so we're going to share just a few tech apps and simulations. So one you've probably heard of or used before that I use all the time in physics is PhET. So as you know or may know, that physics and math go hand in hand and you can't have one without the other. And what I absolutely love about teaching physics is making that connection with mathematics with my students and giving them multiple representations and multiple models to help build their mental model, their conceptual model of an idea. So with that, just a little note there is that's what clicked for me is I remember being in college and taking like a physics course, and it wasn't until we made a connection with science and math where I was like, oh, that's what they meant in math class. So I'll talk a little bit more about that. But since we're doing remote learning, PhET is great to use, obviously for remote learning and data collection, and their simulations to help build those models. However, I would also use them in regular face-to-face instruction as well. So with that said, a few things. PhET, there is a ton of different resources for different sciences, not just physics, but then there is also simulations just for mathematics. So take a peek at what that looks like there. And I'm not in presentation mode, so I apologize for the Google slide. So I know that it could be very different on how you want to implement these into your class. It might be an exercise where they're kind of playing and exploring, and then they learn the concept and they have kind of a foundation or some background knowledge, or maybe it's a tool to go along with the concept simultaneous while you're teaching that. So totally up to you. There are various ways that you can use these, but there's a ton of different simulations for different math concepts. Now, what I wanted to show you for physics in particular is just talking about our first unit. We always cover motion. So, and graphing motion can get incredibly confusing for students. So we typically start with a position time graph, and what is position, distance, displacement, and actually acting that out or doing something physical to match this graphical representation. But it gets kind of confusing when students are just looking at a graph and they're like, and then I ask them, what is happening here? What is the object physically doing? And so there's a lot of confusion, especially when we look in here and we're looking at graph 3, and we have a negative slope, and most often students will think that means that an object is slowing down. So then I'll take it a step further, and it gets even more confusing when we start talking about a position time graph and now a velocity time graph and an acceleration time graph. And all of these, by the way, mean the same thing as far as physically what an object is doing. So one thing that I like to do is a moving man simulation. And I would have to use something like this because now we're not in person for them to actually physically do a lab. So this is a good one, and there are several others where they can mess around with changing different things to look at what a graph would look like for velocity, speed, acceleration. So I have a couple scenarios here. Scenario A man moving from the center of the screen at 0 meters to the house, which would be in the right direction, 8 meters at a slow, steady pace. And so I'm going to go ahead and do that. And so what I might ask students to do is to actually predict what some of these graphs would look like first, just looking at position versus time and velocity versus time to start. So after maybe they've done some experiments or collected some data and they have an idea of what velocity even means physically, and this rate and what we're comparing, and maybe we've done unit analysis, those types of things. So having them make some predictions, and then I would actually have them do this with a simulation, just to help build and strengthen that model. So moving as much as I can to the right from 0 meters to 8 meters at a slow, steady pace. And
So
then
you're moving him?
yes, so I'm just moving him with my mouse, and then I stopped for a few seconds, and you could see the timer here moving. And I'm gonna go ahead and stay stopped for a while, and I know that the little task didn't tell me to do that, but I can zoom in here on my graphs if needed. It changes the scale, you can see on the left side here. But then they can match that to what they had predicted. And I'll be honest, that was not very good and very steady of what I had just done. But let me try it again. So I'll reset. And I will move to the right at a slow, steady pace. See if I could do this a little more steady. And there we go. So really what we should have seen, especially if it was constant, this would look linear here, and it flattens because why? What is the object doing? Well, that's my position now for those last several seconds. But here, really, and usually we use Logger Pro to graph some of this data, or we connect it to some vernier devices such as a motion detector, and we'll have some nice clean graphs. But this is what we're working with for now. So if you were to draw like some sort of line of best fit, it would probably look horizontal here, somewhat, I guess. But basically that's because I'm not accelerating. So the slope of a velocity time graph is your acceleration, and it's not accelerating. That's I try to go at a slow, steady pace. And what's nice is if you move them back in the opposite direction, and I can move them really fast. And what I like about that is you see, and you are physically moving the man fast, and you see if you have a negative slope, that didn't mean that he was slowing down, it just meant direction. So same thing here on velocity versus time at the bottom. When you have negative, you're down in this negative area, that just means direction. So doing this, messing around with that, playing around with that helps build a better conceptual model for students. So that's one way that you can incorporate, incorporate some sort of simulation to help strengthen a model. But another thing I want to show you is actually a simulation with gas laws and gas properties. So here, I'll send this to you in just a second, but I would actually ask students to collect some data. So this might be something where I set them up in small groups in Zoom or in Google Meet, and I ask them as a group to collect some data, and then they would graph that data, and we'd come back together as a whole class and then see what it looks like as a whole group. You know, one experiment isn't enough, so we want to have a scientific community report in and see what they have. And so I can still do that remotely with a simulation. So I know there's only 3 of us on the call, but what I'm going to do is put this in the chat box, and you can just copy this link, paste it into your browser, and you'll be able to open this up. When you do, I want to point out a few things. You'll automatically be put on the hot air balloon tab. So what you'll want to do is click on gas properties, make volume a constant, and then my task to you is to put in 200 heavy species, and you can press the play button. And what you're going to do, the variable I want you to change is the temperature. So you can add temperature, really you're adding energy in the process of heating or removing, you can do that. And I would like you to pay attention to different temperatures, 5 or 6 different temperatures. And then if you could just jot down what your pressure reading is. So I'll go ahead and put this in the chat box.
Okay, so to clarify, put it on the gas laws, adjust the temperature, and then record the pressure, I think is what you said, right?
Yep. So let me see here. Get this out of the way. All right. So you'll select gas properties. You want to keep volume as constant because you can change the size of the box. And we're going to work with, we'll also keep the number of gas particles. They call them heavy species in the simulation. We'll keep that constant at 200 as well. Now, if this was with students and they said, well, what if it was only 100 gas particles or molecules? I would certainly let them explore that. That would definitely make for more interesting data as well, I believe. So same thing with volume. Could we change that? And there are different gas laws that we could explore here, but for the sake of the call, let's just try this one. And we can all collect data and then come back and see what we have. So let me put this into the chat. Go back to my Zoom here. Okay, there we go. Okay.
Should work.
And I'll go ahead and do it as well and collect some data.
Could you put those directions back up, please?
Yeah.
Volume. Thank you.
So we just leave the light species blank?
Yeah.
So it stops when it's done?
It kind of teeters around a pressure. So the best pressure that you can, is that what you mean?
We pause it when it becomes more stable, the pressure?
Yeah, it's as stable as you can kind of get it. So I'm like 1.01, 02.
Oh, the temperature is on the top.
We're supposed to vary for the temperature though, right?
Yeah, you'll be changing the temperature only.
So once they get one sample, it says get 6 samples, right?
Yes, so you want to change the temperature 6 times. Anything you want.
And as the temperature oscillates, just take the best guess, right? Or the pressure oscillates.
For the pressure, yeah.
Well, that's realistic. It even is.
When I try to move the temperature up, it doesn't stay up. It comes back down.
Yeah, so, oh, your temperature changes?
The heat control?
Yeah, the heat control, it will. As you're adding, it'll have the little fire underneath.
Yeah, oh, I see. And you let go and it goes back to 0?
That's fine, but you'll see the Kelvin, the reading in Kelvin, and it stays there.
Oh, I see. So if you hold the heat up, it'll stay, the burner will stay on.
Mm-hmm.
Okay, got it. We supposed to be writing this down or?
Yeah, if you could write a few down, because we'll want some data that you can actually use.
We will use it later in the presentation. So, yeah.
Well, I'm sure glad I'm the only participant.
We appreciate that you're testing us out.
Yeah. Thank you for coming. And 6 should be sufficient. That's what you said, right?
Yeah. And usually I mean, with students, I require 10 or more, but I figured with 6 and just getting a gist of how you can use other technology and apps, that was fine. And Any observations anyone wants to share out with your particles, your gas particles that you notice whenever you add or remove energy?
Well, the cooler it is, the more less pressure there appears to be. That's one observation.
What about what about the physical behavior?
They're not as excited.
Yeah. Yeah. Not as excited. Moving slower, closer together. If it's colder, as we would describe.
Oh, wow, you can keep going. I did not know that because I wanted to see what happens with the temperature. I have it at, I think, 1,401 kelvins. I just wanted to see see if the thermometer burst. It did not, but that's okay.
So I do explain to students it's a simulation.
Okay, I got the 6 down. Temperature and pressure.
Awesome. All right.
James?
So,
I'm almost there.
okay.
Okay.
So I had mentioned earlier that in the physics labs, we would typically use Logger Pro software to graph, or there's Graphical, which is an app I suggest students to put on their phones. I'll have it on my phone and I can quickly just input my data and do a line of regression. But Frank had showed me Desmos, which I didn't realize you could also use. So our independent variable that I had changed was temperature. So what I would like you to do is actually input your values and then do a line of best fit. So I will say with Desmos, that's new to me that this is so cool, is I thought you could only put in functions and it would just graph them for you, but you can press the little plus sign in the upper left-hand corner, insert a table, and you can input your values. The one thing that I don't know if it's possible to do, Frank, is to actually name your values like you can in Logger Pro. For example, it's really useful for students to actually see here that this represents my temperature in degrees Kelvin, especially when we do like a unit analysis from like with a
label the axes, not the table, I don't think.
Oh, okay.
Yeah. So what we could do then is to relabel the axes where you say X represents the temperature in Kelvin and the Y represents and that would be under the tools.
Yeah.
Okay.
1.6. The notion of regression is also interesting, but I might be jumping ahead.
When you click the little magnifying glass, it'll scale it automatically
Nice.
on the left. There you go.
Oh, perfect. See, I'm learning. That's some pretty nice data.
But you're pretty close to mine.
Cool.
And Frank, does your graph show something similar?
Well, let me take a look because I switched my tab to Desmos. I'm going to switch back to Zoom. Oh, wow, that is really a straight line. Mine actually had one bump in the road. But let's see, so you're taking Y1 and you did some sort of a mark there. I'm not quite sure what that is. So can you explain what those mean?
Which mark?
Well, that thing that looks like a tilt, or it looks kind of like an Anye symbol.
Oh, yes. So I had just learned that, so I used y equals mx plus b, and I learned from you, Frank, that you can write your subscripts with an underscore here. And then you press the arrow, I believe, and you'll get out of the subscript. So with that, you can see that M is my slope here. So I have 3/10,000,000. With my, and then I like to have this conversation, of course, with students is what does your B, your y-intercept mean? And should it actually go through 0? I mean, if we had, no temperature, would we have no pressure? And is that true? And what would that look like? Those types of things.
Nice. And then the Y1 and the X1, those are picking up what's actually in the table.
Yes. So I guess so a couple things. One is with physics, what I like to do is make sure that students are able to use the technology. They can certainly do things by hand, and that's perfectly fine. But I think also being able to use the technology is pretty important. So there's that, but then also having that simulation or some sort of physical experiment that connects. Because with me, all I remember is input output table. And this was in high school, and it wasn't until college that I had mentioned that the light bulb went on. So I was thinking, okay, up 1 over 2, up 1 over 2, and I just got to follow this pattern. And what does it physically mean? I didn't even know it was supposed to physically mean something. So it was a real eye opener for me of how important or what a great connection you can make for students by attaching it to something like gas laws or position in time or whatever you can experiment with. So but other than that, that's what I have for you for PhET. But we can have a nice little segue into Desmos. Frank, if you're ready.
I am.
Okay, let me stop share.
Okay. You guys can see it okay?
Mm-hmm.
All right. So I think this is where I want to be. So one of the technology tools that is really helpful in a real time is to do the graphing calculator. And we just did some impromptu work based on actually recording the table and looking at investigating the relationship between temperature and pressure with the gas laws. And so you can go to desmos.com and either go to the graphing calculator, which is on the top that you see here, or you can also do some pre-built activities. Those are really two options that you have. There are other options that Desmos as a calculator has, which is the geometry tool, the scientific calculator for a function calculator. For today, we're going to really explore the graphing calculator. We had a taste of what is possible with the experiment that was just done. So it's really good for impromptu work. We just created a table and we investigated their linear relationship between pressure and temperature. A couple of things also is there's some interactive graphs. So like perhaps you do part of it where you use it to illustrate a concept. So for example, I've done it for trigonometry, and each one of these links that you see in this PowerPoint presentation are links that I have shared publicly. Do you guys have a preference whether you want to do the Ferris wheel, the normal distribution, or Maclaurin series?
No preference.
James, do you have a
How about
preference?
the Maclaurin series?
Let's do it. Okay, so Maclaurin it is. We have chosen Maclaurin. So right now you guys can see the Taylor and Maclaurin series window, I believe, correct?
Yes.
Okay. So as we're looking at this, there are a couple things that we're going to do. I'm going to first of all just turn off a few of these things, and actually this has a very nice connection to physics. So I'm going to show it. So one of the things, when we're looking at a Taylor or a Maclaurin series, what we're doing is we're representing for example, trigonometric function or some other function as a series of adding a bunch of terms of a polynomial sequence. And there is a process in calculus that lets you determine what that is going to be. What is that infinite sum? So in the case of sine of x, this is our regular sine of x. And one of the things is in physics, they often say that for small angles, sine of x is approximately equal to x, give or take, or the sine of the angle is approximately equal to the angle. And actually that does come from a Maclaurin series. It's just that you've only shown the first term, but we can do much more accurately than that. So for example, I go to 1, and we were looking at that. I guess I need to even go further back down to 0. Okay, 0. So right here, when we are just saying sine of x is equal to x, we have k being 0, and that's equal to x. But what would it happen if we were to add more terms? So what we can do is have students investigate what does it mean. So the first part of it is having them write it as an infinite sum. So what we're really doing over here, and I'm just going to add an extra one in here, is what we're saying is, okay, we have, let's say g of x is equal to the first, which was x over 1, which is our infinite series. But then what we can do is add another term to it. And that gives you a slightly better approximation. So that is when k is equal to 1. What if k is equal to 2? So what we can do is notice that now the function goes a little more. What do you predict is going to happen? Let's be a class. So I would ask students to, okay, as k changes, what do you notice happening? So let's say k increases. And let's make it increase more. So the red function, I'm going to turn this off for the moment. The red function represents the original sine curve. And this is a polynomial approximation. What would happen if I increase k even more? And more, and more. And so what ends up happening, as we add more and more terms, it becomes like the full sine curve. So what we're doing is each one of these terms in summation, we're adding another term. So like this is when k is equal to 0, k is equal to 1, and k is equal to 2. And one of the things we can also have them do is actually test to see if that matches up. Oops, not that. This and this match. So they also can tell. What I usually have them do is first write the polynomial for a few terms, then see if they can write the series in summation notation and see if they can get it to match for the first few terms, and then crank up k and see what happens. So the physicist oftentimes will only use the first term for small angles. But as you add more and more terms, this polynomial approximation gets better and better, and you can actually use it for larger and larger angles. Now, oftentimes that makes the mathematics of the physics more complicated, but if you need something beyond a small angle, knowing where it came from, which is a Maclaurin series, is useful. So they have other investigations, and for example, they can also study cosine of x and also e of x. So this is an example from calculus after they've learned how to write functions in summation notation. Now, do you guys want to play with it? If so, I can share the link that it goes to. And if you look at your chat window, that's the link to that particular series.
Got it.
So play with K and see what happens. I probably did this all wrong, and that I should have had you guys explore it first.
I really like that you can check and see that they actually, it aligns.
Mm-hmm. And that's one of the things that I love about Desmos is it takes an abstract idea of like, okay, yes, you can form an infinite series, but how does it actually work? And what happens if you only add a few of the terms? How does that affect what you're getting as an approximation?
Mm-hmm.
And other questions in math, like how many terms do you need to add for the error to be guaranteed within such and such? Do I need to put
That's the part that I like, where you can figure out the error.
Mm-hmm.
You're if you're not, you know, trying to find the sine of, I don't know, 1.3 radians or something, you can set A at 1.3 and then figure out how many terms you need for how much accuracy you want.
So yeah, there are a couple of things that also, in terms of planning for it, this is telling you how much error you are depending on where you have your A. Like for example, A is equal to 5 at the moment. But if I go further down, I can also adjust it. And it actually tells me, like, for example, if I'm exactly 1 radian and I've gone out to up to k equals 2, which means you're going all the way up to x5 over 5 factorial. When we're at 1 radian, the error is negative 0.0019 from the true value of sine of x, which isn't bad. Now, each one of those ones which you see is currently not highlighted just tells you where we are function-wise. You can zoom in to see. If you click and zoom, you can see how the function, how close it is. And if I were to move, and if you move A further, you can then also see how the error changes. So for example, move A to, with k equals 2, so just k equals up to 2. And let's say we want to go to 2 radians. So A is representing the angle measure in radians. And the question then is how close is the approximation, the polynomial approximation to the actual sine of x? And is that acceptable enough for what you're trying to do? Is it good? So is it good enough to be within about 2 to 300ths of the true value of sine of x? Is that okay? Or do you need to add more terms because the error is still terrible, depending on the precision you need? Mm-hmm. For example, if I'm at 3 radians, the approximation that's a terrible approximation. Now you're off by 0.38, give or take.
You could put labels on those points so you could actually see the function values on the graph, right?
Mm-hmm.
Is that?
So let's do it. So let's see, we're looking at sine of x. Oh, wait, I just need to put it right here. So we're going to put a label. So this one over here.
There you go, yeah.
What would you guys like to label that top one? Is that the approximation, or is that the actually I'm treating you guys like students, never mind. It's like, okay, which one is which, right?
That's the red one.
The red one is the approximation. And the blue one is, I thought the red one was the original one. Let's take a look.
Well, the red line, but it's a red dot.
Yeah, I was looking at the graph. One graph is red, the other one's like, I don't know, red again. The point is blue on the red graph.
Yeah. On mine, one of the lines is blue, the other line is red, and then they've transposed the color of the dot.
So let's do this. So let's say we hate the color of our dots right now. We could, for the purpose of the pedagogical integrity, let's change the blue dot to the blue function. And let's change the red dot to go with the red function. And now it actually seems logically consistent.
Oh, yeah.
The only thing I'm wondering is, why is there a red thing? Is because it's because I'm showing this one as well to show that the series, which is in blue, is the same as the approximation. So I'm going to turn this off for a moment. And now you can tell who it is.
There we go.
So one of the things is one of the nice things about this tool is when you see graphs identical or overlapping, that means that they're equivalent.
Oh, cool.
And it definitely is useful also for coincident lines, like, well, is it the same? And so over here now we have the approximation, and we also have, you can also have it label just the point. So if I take this off, and I were to click on the dot, label and label, it will actually tell you what, so when at 3 radians, the approximation is, the value of sine of x is 0.525, but actually the approximation is 0.525, yet the actual value of the sine function is 0.141. So then the question is this a good approximation at 3 radians? And hopefully students will say, no, it's a terrible approximation. However, if you're, let's say you're at about 1.5 radians, give or take, well, that's actually pretty good. They're very, very close to each other at that point. and you actually see the exact error below. So that's one way I use it. In other words, creating some few lines of codes and then having them explore what does it mean when you move, when you actually adjust the parameters, what happens? And then making judgments like, okay, do you think this is good enough? How good, if we're talking about relative, we're talking about absolute versus relative error. Is having a relative error 2% a good thing or not? Depends on the context. So that's one example. Now, another example of Desmos. So another thing you can do is explorations. So we have something partially composed and having students. So there is you actually built something to have students investigate what does it mean to alter the parameters. And it already does the calculation. So you're really using it as a conceptual tool. The other one is to actually help them in exploring what types of patterns they can see, similar to the approach in physics where you're taking data and then seeing what happens. So do you guys I'm going to do the ones with coins for the moment. So you got that. Okay, what I'm going to do is in the chat stream, I'm going to share a link to another app that I built. So I hope you guys got it through the chat. And that is going to open up the coin simulator. So you're going to see something like this, where you're given a scenario. A friend gives you 10 coins, which consist only, so what it is, this is a partially finished activity where they have to fill in the blanks. So oftentimes, like for example, when you're using worksheets, this is an analog to it, where you have part of it like as instructions, and then the rest they have to then work on it. So in the case of the coin scenario, a friend gave you 10 coins, and I think you guys are only seeing the browser screen, correct?
Yeah, Desmos, okay. Yeah.
I've sometimes been bad and I've shared the entire screen and then it's just a disaster how many windows are open. So I'm glad it's only on that one. So what it is from an instructional point, you can actually upload images like so, not that. You can also save files and then share them with the world, which is pretty neat. But over here, you can upload an image and perhaps you already had it. So what I did is I uploaded this as an image and that becomes the instructions that you have posted on the graph. So one of the things is giving him instructions, and the first instruction, it says if friend gives you 10 coins and it consists of only nickels and dimes, table below list 5 possible combinations that have coins that may occur. And because of the way Desmos is, you need to kind of tell him like, okay, let X represent nickels and let Y represent dimes. So what I'd like you guys to do is to come with 5 combinations of nickels and dimes that produces 10 coins. Create a table and add it to your, and what you'll notice is as you start adding the table, something should happen in your, so let's see, if I have 3 of one type, then I have 7 of the other. I'd like you to try this along as well.
Okay.
And the only requirement I ask is make sure you're, well, actually you'll see something if you do it wrong and you over or underestimate the combination of the two. And I'm going to do that. No, I don't want to do that. Let's see. So then I'll ask, students, what do you notice? If they did it all right, they'll see a really neat pattern. And then further in the discussion, I'd ask them, can they write an equation that represents that that there are 10 coins that and so what I'd ask them to do is create a blank line and write what they think is a way that relates to the nickels and dimes, knowing that you have 10 coins altogether. So you can add an equation, or in this case add an expression. And what's nice about Desmos is it does not have to be written in a particular form, so it lets them create intuitively what they think is happening. To cut through the chase, I'd let them play for a while and see what they notice. If they do it right, they'll have a nice visual confirmation that the situation that they are modeling goes right through the dots. So that's all possible combinations of X and Y nickels and dimes that produce 10. Then we talk about whether are there parts that are realistic or not. Can you have negative coins? Does it make sense to have a partial coin and those kind of things? But in terms of a model, the line does pass through the particular points that were plotted. So do you guys have a chance to try out yours and see if it works?
Yeah, I did. I do have a question about those gray dots on your so your X and Y intercepts. Are they gray just because that's where they lie? Because
You mean this over here where the,
no, click again on the.
oh, where the intercepts are themselves here?
Is that why they're gray? Is just because they're intercepts?
Yes, so it does actually
Okay.
show critical points and it also shows intercepts.
Okay, I was just wondering if they were gray because it wasn't possible.
Yeah, it will do what I call highlight or landmarks. So it
Okay.
is also possible. You can also click on any of these points and it will, as you go
Well,
through 2, 3 as well.
I just meant it's not possible if you have 10 coins, it's a combination of nickels and dimes. It's
Mhm.
not possible you wouldn't really have ever data on your intercepts,
Mm-hmm. If
right?
you're
So,
working, so then the question I'd ask, since you guys are my students, what would it mean to be 0 and 10? What does that actually mean in the context of this scenario?
well, you identified dimes as your Y variable. So that would mean you have 10 dimes, which isn't possible because you said you have a combination of nickels and dimes.
Yeah.
I thought that it had turned gray because it knew your scenario. I thought Desmos knew your scenario and they knew that those dots right there wouldn't work. That's why I was like, oh, that's so cool. How do they know that?
So a couple of other things that we can do is also to adjust the domain of this function. So we would say, well, is it reasonable to have negative coins?
Mm-hmm.
You can do that by adjusting. So what we do is we would make it as a set. So you actually restrict your input. So 0 is less, because we just said we're not going to accept the possibility of 0 and so it's less than, less than 10. And notice right now that the line segment's shorter. And even though this technically is still there, if you go on the function itself, you will notice it's not defined when you hit 0
Oh, cool.
because it's outside of the domain.
That's
And then we
really
then talk about what does it mean to have intermediate values and is that realistic? So a model is just that, a model. And the question then is the model useful? So in the second part of the activity, and now what I say is, okay, now what I asked them to do is then to turn off the scenario where coin scenario 1, okay? And I asked them to click on coin scenario 2, the little circle. And we leave this up here. And a friend gives you a batch of nickels and dimes, whose value is 85 coins. In the table below, there lists 3 possible combinations. So you need to create a table and then list 3 possible combinations of nickels and dimes that produce 85 cents. So we would add another table and let you guys play and see what you get. I'm not giving you a restriction other than the value of the stack needs to be 85 cents.
So if students knew how to quickly come up with an equation, could they?
Oh yeah. And then I would let them know. I didn't mean to cut you off, sorry.
No, I'm just wondering, like the works of Desmos, like could you input a bunch of X values and then it would tell you what all your Y values would have to be? Is that possible?
Yes, you can create a function and turn it into a table. So we can, if you have a function model, then you can actually convert that to a table or even a graph that would turn into a table. We'll try it.
So your second table there, you want you just want it to be a value of 85 cents, right?
Yeah.
Okay.
And you can also move your tiles around in Desmos. So like you're not stuck in the order. So you can always move them around if you find it more convenient.
And you said X were nickels and Y was
Yeah.
dimes, right?
Yeah, let X be the nickels and let Y be the dimes. So, okay, with 1 nickel, 8 dimes works. That's enough. And then the second thing I would ask is once they've come up with a table, they'll say, oh, look at that. There's another nice pattern to look at, right? It looks like it's also. And so the next question I'd ask is, okay, think of an equation that just represents the value of having 85 cents. And there might be a couple of different solutions depending whether they think of it in terms of dollars or in terms of cents. And wow, there's 2 cross. What a miracle. No, that was intentional. So then the question, you can then ask them to click on the point where they intersect. And what does that mean? What does that point of intersection mean? Notice I didn't actually stage what does it mean, but I'm asking the question then to them is like, okay, so what does it mean when the 2 cross at 3, 7?
You satisfy both scenarios.
Mm-hmm. So the pile of money is 85 cents and you have 10 coins at the same time. So that's simultaneously true.
Mm-hmm.
So it's kind of fun to investigate. So going to your question, let's find out. So I can create, now if I have it solved in terms of y, I can create a table, which would then predict. So you have to create a function for it to create because what it's going to do is as you fill in x, then it's using y as the output. So let's see, if I were to solve this, do like this. It's kind of interesting is, I'm not saying this is a traditional way to solve an equation, but one can actually see that as long as you are creating equivalent statements, it should still produce. So another thing is are these the same? Yes, because they still are graphing. Well, that doesn't help to see them in the same color, does it? But notice that they are equivalent because, no, I don't want to do that. As I turn it off, it's still the same line. So we know we did our algebra solving process correctly.
That is so cool.
So I do use this as a way to graphically verify. One I use it for is identities. Like, okay, you created 2 different, you prove that sine squared plus cosine squared, the sine squared of an angle plus cosine squared of an angle is 1. Well, enter in sine squared plus cosine squared, then enter 1 as your other function. Do they match? So you could show that their 2 are equivalent. In this one over here, let's make a copy of it. Well, I don't know what I just did there. That was goofed. I imported a graph. Did I just lose my example? I don't think so.
Oh, maybe you did.
Well, that's terrible.
You have a completed one saved? I always do one blank one and one saved one.
Yeah. So I know what I wanted to do. Yeah, I did have it saved. So that's the good news. Let's just do that. It's funny. So I'll just go back in. So one of the things you can do is you can create an account. And what that lets you do is it lets you save the different resources that you create. Okay, so here's where we were, right? Julie. And one of the questions that you had earlier is, can you create it was 85 minus 5x, and I believe that was divided by 10. I think that's what we had as a solution, correct? Then I made an error when I was copying, but I'm going to do Command C. And what you can do is you can convert this to a table that then calculates your different coins. So like, for example, when there's 0, what does that become? When it's 1, So if you have 0 nickels, how many dimes does that necessarily mean, right? So 2 would produce 7.5, which doesn't make sense, but 3 would produce 7. We also had 5, which then produces 6, and so on. So you can have the equation actually also predict what the value needs to be, and it starts adding them into it. But you can also skip, like, let's see, 0 is not possible. So when you have 1 coin, it's 8, 3, it's going to be 7. So if your equation is correct, you can actually test with a table to see, is it regenerating or reproducing the same values that you originally had predicted when you made your table. So when you had 1 nickel, you should have 8 dimes. When you have 3 nickels, you should have 7 dimes, and so on. So this also gives a verification step that the equation that they produce is correct. And what I do is I take the equation that was proposed, I copy it, and I'll show it again. And what I will do is, and I think you guys are still seeing my browser window, correct?
Mm-hmm.
I would turn it into a table, and then you can just adjust the values that you're doing it for. So it allows you to create the function that describes it. So that's a little bit about Desmos. One other thing that you can do with Desmos, since I now am logged in, and I'm not gonna, I mean, I could go back to the PowerPoint, but this was the next PowerPoint in the series. Yeah, I want to leave the page. I had enough of the coins. It's awesome, but not that awesome. So over here, we have teacher activities. So you can also do pre-built activities. And for example, it has collections that Desmos distributes for free. And and you can put it in your own private collection and add to it and also edit it. So like, for example, Desmos classroom activities. And what I did is there's ones that they provided, then I made a copy, and it lets you edit it or use it as is. And so what's going to happen here, so let's go down. I'm going to do copy of the marble slides, which is kind of fun. This is something that you could do with, so you create a class code and you share it with your class. And as students log in, it would record what their work is. So I'm going to edit the draft. This is not a published one yet. Let's say I want to do a preview. So the idea of the marble slides is to, you have a ball and it rolls. And so that's not very exciting, but then they ask you to, let's say you're trying to learn linear equations. So what it is they have a whole library of different types of applications in linear functions, exponential functions. The marble slide is just one that I liked, but there's so much variety of what you can do. It's just a matter of patience and looking what is a good fit for you, what you're teaching. And you can create these. This is just a preview mode, but let's say I wanted to see what it is, and they would show what the student's work was and what their solution is. So then I would have them exploring, okay, now when you're in this particular slide, and this is letting them investigating the meaning of what is it to have an intercept or what to do with a slope. So like in this one, what adjustments do I need to make for this ball to roll down and get these stars? And I would, of course, give a strategic pause and wait. And actually what they would really be doing is I'd be having them do it themselves and then go into the groups and see how they're doing or seeing how they're working and just talk to them individually as they're working in teams with a marble slide code that they've done. Or they can do them as an activity. The thing is, once they get going on these, they usually just want to ignore you and work through and get done because it's very reassuring to actually do this. So in here, let's say I change it to -1. That's not good enough. -3 is too much. And then I would launch. And they have 23 more slides to do. So it gives them practice of studying the different effects of changing the different parameters in a linear equation. It tells them you can also reset if they don't like what they did, and so on. And these are pre-built. So Desmos does have some pre-built activities. You can build yours yourself, like you saw in the previous example, or you can use it impromptu, like here's some data we had, let's put it in a table, let's investigate what it's like using a linear regression, which is what Nicole showed earlier, how one does a linear regression with a table of data. I'm going to stop sharing. And I'm going to ask if there are any questions from the assembled group over here. Or thoughts. How might you use it in your class? I'll ask that to both of you.
Yes, I love I didn't realize that I could have students put in two functions, manipulate one of them, and show, like in the graph, that they overlap because they mean the same thing. That is so cool.
I like the hands-on activity, especially the one you just showed about changing the slope and the y-intercept to accomplish a goal.
Mm-hmm. And what I've noticed with those tasks is once you get them going, they just ignore you, which is great. I mean, in other words, they really engage with the activity, and they are constructing their own knowledge, and you don't have to tell it to them. They might have questions if they're stuck, but they usually figure it out, and they're very driven to actually get through the task. And is actually through interacting and making mistakes, they learn many of the things. So Desmos has learning resources where you can learn all the commands. This is just scratching the surface of what's possible. You can actually write some really sophisticated code. And there's a lot up there in Desmos that's in the community where someone has built an app, like an animation or even artwork. Desmos is used in ways that you can, I think, this is just the bare minimum of what can be investigated. I don't know, Nicole, do you have time to play with this one as well? This is the Wolfram demonstration project.
I haven't yet, but it's on my to-do list.
Okay.
This week has been a little crazy.
Oh, definitely. So one of the things that one last resource that's helpful for visualizations is the Wolfram's demonstration site. And for example, I've used it to have students explore what does it mean to slice a solid of revolution, or to even rotate, or to investigate the unit circle. And each one of these links provides a free resource to let students investigate. Oftentimes, all it requires is just doing a search for what you're looking for. It probably exists. And sometimes you have more than one choice, so then you pick the one that really fits your lesson the best. And I mean, at this point, we can get to the evaluation, or I can show you what demonstrations look like. What would you guys like to do? Or would you like to find one of your own? Have you, and it does span multiple subjects. It does math, it does physics, it does computation. It's really a lot of resources. And I found it helpful, especially in trig and calculus. So you guys have so you get to choose where the next part of this goes. Or we could have a discussion about, James and Nicole, what other resources have you used that you have found helpful for doing simulations or applications that you'd like
I've used Desmos, I'm sorry, Wolfram quite a bit in calculus, but I haven't looked at the teacher activities in Desmos for quite some time, so I'm kind of distracted looking at all the stuff they have there.
They've really built up in the last few years a lot of cool resources.
Where was the one about the stars that you just showed?
Oh, sure.
I don't mean to get you off topic. Sorry.
No, I mean, at this point, the only next step is the evaluation, and that's kind of like, it's not that exciting. Although we appreciate your evaluation.
I do like the Desmos. I'm sorry. I do like the Wolfram for three-dimensional stuff.
Mm-hmm.
If you're not familiar with Maple or any of the 3D graphing software, if nothing else, this is a really nice tool to demonstrate, especially Calc 3.
Mm-hmm. So I can try to do, try to get the link, see if I can share that. And then we can play with Desmos. So if you want to play with Desmos, let me take you to that one first. So with Desmos, if to test it out.
Oh, there it is. I found the one I was looking for.
Cool. It's called Marble Slides, and there's different versions. So what happens is when you're in Desmos and you're trying to find it, so let's say you go to teacher.desmos.com. I can show how you build a collection. And then if you're trying to add to your own personal collection, you just want to create a free account and use it. Every one of these resources is free. So it does give featured collections. I type Marble Slides. And they've been translated to multiple languages. So Desmos is pretty, and you can do different types of activities. So let's take a look. So you could do periodics, you can do exponentials. When I was looking for the linear one, because I do remember, I learned about the marble slides at a conference. Slides, linear. It actually found the copy of mine because I'm logged in, but this is the one I actually took it from. Okay. And then you can make you can adapt from it. And then you add it to your collection by creating a collection. You can also share it, but no, that's not what I want to do. You can add it to your collection and you would just put it in here and then it saves it. So anything you like, you can kind of keep bookmark on it in a way. But they got lots. And to access it, you'd go to the teacher page and then you'd be looking through here, what do they have available. The other one I think you had mentioned is the demonstrations, like seeing how that's like. So that was the link that was for the volume of revolution. And so oftentimes what you'll see is it initializes it, and that's normal. And then after that, you can use the sliders to make adjustments like here. Let's say I want to separate the slices. What if I want to bring them together? You can do that. There's a little bit of delay just because of internet, but you can move the slices together. You can widen them, or you can narrow it. In this case, I think I just made it more narrow. And you can also change the number of slices. So if I want to reduce the number of slices, I can make them really big wedges, or I can make it really, really tiny, like that. And you'll see like the original function right there. If I were to push it back together again, let's say I want to push it back together there. You can also make you can actually squish it to see what it is. So oftentimes you'll see like make a volume revolution around a piece of it looks like a sine function and see what that looks like and what would the volume be. Other things you can do is if you go to the main page itself, if you're trying to find an activity, and then just a matter of experimenting with it, you get always the really awesome looking page. So you can click on mathematics, you can click on any of these. Let's say I go to mathematics, it'll give options of what you want to do, and then you can either browse, or you can, like if I'm looking for something in algebra, I'm looking at complex numbers, it lets you do different things, and it also lets you look for, say I want to look for a Mobius strip. I actually don't know how this is what is gonna happen. A Mobius monorail, ooh, that's cool. So the point of this is you can get lost and just like look for stuff and let people, let your students really just investigate what happens. And that's all I have. So you guys got to see the demonstrations. We got to play with Desmos, both from a data perspective and also creating interactive graphs. And we got to look at data sets and real life simulations. What questions, James, this is kind of a weird one. What questions do you guys have? Oh, there's an audience of one at the moment.
I don't have any questions. I mean, what's nice about this program or Wolfram demonstrations too, if you happen to have Mathematica, is it Mathematica? Is that the platform that it's based on?
I believe so, yeah.
I have an older version, so you can download them and then tweak them a little bit if you need to.
Mm-hmm.
I don't really have any questions, just some things to explore further. It's been a while.
I'm not sure exactly how to close the session out, other than please do evaluate it. I guess that would be one thing, right? We do want your feedback. I'm going to put the feedback in the chat. We will be probably only one evaluate. Actually, we're only holding the session once, by the way.
I guess I better do a pretty good job evaluating you because you know who it came from. It was perfect.
Best session ever. And again, leave it on Yelp too.
5 stars, 5 out of 5.
Okay. So that is the session evaluation link. I don't know, Nicole. I'm out of ideas at this point.
I know. Sorry, I got stuck with Wolfram because it's so cool, and I keep looking up different models for physics stuff.
It is, yeah, it's easy to get lost in these. They're fun.
Yeah.
So yeah, that's all we have for you. Thank you for coming.
Good job. Thank you.
All right. Thank you, James.
All right, you guys have a good night.